Welcome back, Virtual Earth and Space Science. We're continuing our discussion of stars. This time we're going to focus on magnitude and brightness and luminosity. So the classification of the luminosity of stars began a long time ago. The earliest one I know of is an ancient Greek guy named Hipparchus. Over 2,000 years ago, he looked up and started giving stars numbers to define their brightness. The brightest stars he called number 1. And the next brightest, number 2, etc. And you can see an illustration of that in this picture I've drawn here. So it's kind of weird and unfortunate because the lower number means brighter stars. I like to remember it by thinking of number 1 star is like first class, right? It's the best, it's the brightest, it's the biggest. Second class would be not quite as good. Right, so anyway, a magnitude 1 star is the brightest kind of star, and a magnitude 2 is less bright. So, if nothing else, remember that. The lower number means it's brighter. So modern astronomers have adapted his ancient scale and changed it a bit, based on the fact that we used to think that the eye was like a logarithmic detector, and that ends up meaning that as the magnitude increases by one number, the brightness decreases by dividing it by a factor. And the rule of thumb to remember for this is that if one star has a magnitude that's 5 magnitudes lower than another star, then it's 100 times brighter, right? The lower star, the star with the lower number magnitude, is brighter. If it's got a magnitude that's 5 magnitudes lower, it's 100 times brighter. We're going to practice with that and see if that makes sense. Let's say we have a star that has a magnitude of 7 and another with a magnitude of 2. First one you need to ask yourself is, which is brighter? The magnitude 7 star or the magnitude 2 star? Right, you got it. The magnitude 2 star is brighter, even though it has a lower number. How much brighter? Well, if we subtract their magnitudes, 7 minus 2 is 5. The magnitude 2 star is 5 magnitudes lower, so it is therefore 100 times brighter than the magnitude 7 star. It's messed up, I know, and it's just a historical accident because of that ancient Greek guy Hipparchus, and astronomers have decided to keep this crazy system. Magnitude 18 and magnitude 3, how would they compare? Well, the magnitude 3 star would be brighter. 18 minus 3 is 15, which is 3 5s. So it's not just 100 times brighter, that magnitude 3 star. It's 100, 100, 100 times brighter, and 100 times 100 times 100 is 1,000,000. So that's how these kind work. But what if the difference in magnitude isn't a convenient multiple of 5 like that? Well, what about a magnitude 2 versus a magnitude 3? Well, mathematically the way you have to do this is you have to find out what the 5th root of 100 is. And I'm not going to expect you to ever do that, but it happens to be roughly 2.5. So a magnitude 2 star is roughly 2.5 times brighter than a magnitude 3 star. Each difference of one magnitude corresponds to a factor of 2.5 in brightness. Magnitude 6 versus magnitude 4. Of course, the magnitude 4 is brighter. Because the difference in magnitudes is 2, we need to multiply 2.5 times 2.5, which is 2.5 squared, which is roughly 6.25 times. So the magnitude 4 star is 6.25 times brighter. So if you don't have a nice multiple of 5 in magnitude separation, then you have to use this 2.5 to the correct power. Alright, there's a famous star called Vega. It has a magnitude of 0. Okay, it's so bright that its magnitude is below 1, right? Well, the moon is even brighter than that, and it has a magnitude of negative 13. So these magnitudes actually get negative, and the more negative they are, the brighter they are. The sun, which is pretty darn bright indeed, has a negative 27 for a magnitude. But these are all apparent magnitudes. Apparent magnitude means the magnitude that the thing appears to have as seen from Earth. Well, where else? Well, the fact is that something can be bright because it's really, really bright, or because it's really, really close. I mean, you could put your eyeball close enough to a light bulb that it would seem brighter than the sun, but we know that the sun is much more powerful than the light bulb. So in order to standardize things and get a magnitude that actually is a useful description of the brightness that something really has, astronomers invented something called absolute magnitude. if you put the sun 10 parsecs away, that's about 32 light years away, it would have a magnitude of 5, which is not that bright. Nothing like the negative 27 that it appears to have from Earth. And that's what you call the sun's absolute magnitude. The absolute magnitude of something is the magnitude it would have if it were 10 parsecs away. The wimpiest stars out there have absolute magnitudes of around 19, and the crazy brightest stars you could imagine out there have absolute magnitudes of -8. The lowest magnitude star that we can see without a telescope, with just our eyes, is roughly 6. And that is, as far as I understand, as far down as Hipparchus's original magnitude scale went, all the way down 1 through 6. Absolute magnitude is a great thing to know about something, because it tells you directly something about its luminosity, its brightness, its power. But also, if you have the absolute magnitude and the apparent magnitude, if you know how bright it really is and how bright it seems to be, you can use that information to find out the distance. There's some nasty math involved there, so we're not going to do that, but I want you to appreciate that it is possible, if you have the absolute magnitude of something, to use that to find its distance. So we've used the word luminosity before, and it's a measure of the brightness of a star, the power output. And it turns out that the luminosity depends on the radius of the star, the size of the star, squared, and the temperature of the star to the 4th power. It's really, really strongly dependent on the temperature. So it turns out that with stars, red is cooler than blue. It's not like the hot and cold faucet knobs in the hotel bathroom. Red means cool compared to blue. I mean, a red star is hot, but it's not nearly as hot as a blue star. Anyway, a small cool star is definitely less luminous than a big cool star. You see these black circles here. You can imagine that these stars at the same temperature, well, the big one is basically like whatever, 7 or 8 of those little ones. So it's obviously going to radiate more energy. It's going to be more luminous. 2 stars of the same size, same radius, the hotter one, which is the blue one, is going to have more luminosity than the cooler one, the red one. And of course, it's possible that a small hot star, like this blue one here, could have the same luminosity as a big cool star, like this red one here. And so the very most luminous star of all would be a big blue one. It would be both large, with a big radius, and hot, with a big temperature. And the dimmest, least luminous stars of all are going to be the small, cool ones. They're going to be red, so they have a low temperature, and they're going to be small, so they have a low radius. Okay, so these 2 factors, radius and temperature, are both important for the total power output or luminosity of a star. Alright, there are lots of different kinds of stars out there, and now we're going to learn through a few examples how to compare the luminosity of a star to the luminosity of the sun when we change the radius or the temperature. So let's start with a star 5 times bigger than the sun, with a radius that's 5 times the radius of the sun's. Well, because luminosity is proportional to the radius squared, the ratio of luminosities is going to be the ratio of the sizes, or radii, squared. So the ratio is the radius of the star divided by the radius of the sun. That's 5 sun radii divided by the sun's radius. Our suns cancel, and we just have 5 squared, which is 25. So this star, 5 times bigger than the sun, is 25 times brighter. Now let's look at temperature. This is even more dramatic. The sun has a temperature on the surface of roughly 6,000 degrees. That's in the Kelvin scale. And let's say we compare that to a star with 18,000 degree Kelvin surface temperature. Well, because the luminosity is proportional to the 4th power of the temperature, the ratio of luminosities is the 4th power of the temperature ratio. The temperature ratio is roughly 3. 18,000 divided by 6,000 is 3. And 3 to the 4th is 81. So this star with 3 times the surface temperature has 81 times the luminosity or brightness as the sun. So that small difference in temperature made a huge difference in luminosity. Alright, so I hope that you understood how we did those. You're going to have a chance to practice that at the end of the website readings that you guys do. Good luck, and I'll see you in the next video.